Hello, everyone. Welcome to the Geek Narrator podcast. I am your host, Kaivalya Apte. Today, I am joined by Marc Brooker, who works as a distinguished engineer at AWS. And I came to know about Mark and his blog once there was a release of Aurora D-SQL, I guess in December. And I came across his blog post, which is, by the way, a gem of a resource. So I am going to add that in the description. So please take a look. It's really valuable. And I went through the blog. I read about Aurora DSQL, and I became curious. Like, let's discuss this, right? And I invited Mark. So, Mark, thanks a lot for accepting my invitation. And I'm really excited to have you here and learn more about Aurora DSQL. So, thanks a lot for joining. Let's
Yeah, well,
start.
thanks for the opportunity. Super exciting to talk
Awesome.
about this. And yeah,
Yeah, let's start with a little bit of introduction about yourself, your
Mhm.
journey at Amazon with databases, distributed systems. I also know you were involved in EC2 and Lambda and stuff like that. So, yeah.
yeah. So I've been at AWS for 16 years now, 16 and a bit years. I joined AWS just right out of grad school. I did a PhD in electrical engineering, completely in a different field, different stuff to work on, and ended up working at in Cape Town, South Africa, with the EC2 team, um, and that was just a fantastic opportunity to get onto the really kind of early days of the cloud. This was 2008. It was about 2 years after EC2 launched, and there was still these conversations of like, hey, why would I buy my IT infrastructure from a bookstore, right? It was before AWS was really a big thing, and since then I've worked on compute, I've worked on storage, the EBS team, um, and then joined the AWS Lambda team pretty early on in that journey, just after the preview launch in 2014, and spent a whole lot of years working on serverless. So I worked on serverless and with Lambda, with API Gateway, with some of our IoT offerings and EventBridge and some other parts of the AWS serverless portfolio. And around 2020, I moved into the database world, and we can talk about some of my reasoning for that, and I'm now worked with the team that launched Aurora Serverless V2, and then DSQL, and I'm now spending my time on data and AI, and together, because those are two important, very complementary topics, and so yeah, 16 years at AWS, and it's been quite a journey seeing this business grow.
Yeah, fantastic. I mean, there's a lot to talk about, even if we just talk about your career, your path towards your role at Amazon. But that's for probably some later episodes. Today we are going to focus mainly on Aurora DSQL, the world of distributed SQL, how it compares with other options available, and some of the guarantees that it provides, internal workings and stuff like that. I mean, there's so much to talk about, but limited time, so let's get started.
Mm-hmm.
As with any other database, I want to kind of understand the historical things, what was happening at AWS, and how it that database or that idea evolved and how it was released. So Spanner has been there and was publicly announced, let's say in 2017, as their cloud offering, and there were other options like Cockroach DB and Yucca DB. There were some open source managed platforms as well. What has been AWS's journey, and how did DSQL come into picture, and what made 2024 the year for its launch?
Yeah. Yeah, I think there are two ways to do that. One of them is, my personal journey here, and I was in 2020. I was working with the Lambda team, with the serverless teams at AWS, and like a lot of us at AWS, I spent a lot of time talking to our customers about the things that they need and the things they're looking for, and a very common conversation with customers is, how can we accelerate your serverless journey, right? Like, how can we help you move to serverless, move to containers, help you modernize your architectures. And over, the conversation that I had with customers was, we love these serverless things, we love the container offerings, but data remains difficult. There's they're great kind of serverless NoSQL offerings like DynamoDB, but as soon as we want to get into SQL, there is this impedance mismatch between traditional relational databases and serverless, and to an extent container architectures. It's the way they scale up, the way they scale down, the way they handle and think about fault tolerance. And the other thing, as I moved into that data space and started looking at serverless, I started to talk to a lot of enterprise customers, a lot of larger customers at AWS, who were looking at how they can build these maximally resilient architectures. And those customers were saying to us, it's really, we need advice, we need help on building these maximally resilient architectures, things that can survive, large-scale infrastructure failures, can survive natural disasters, and so on. And the conversation that we kept having with them was, internally, we prefer active-active architectures, right? Where, multiple availability zones or multiple regions are writable at the same time. And I can get into why that is, but it's just operationally simpler. And those customers very reasonably said to us, okay, that's great, but you don't have database offerings in your portfolio, in the relational portfolio, that are great fits for active-active. And so there was and is DynamoDB Global Table, great active-active NoSQL offering, but those customers were looking for something relational, something with SQL, and ideally with some compatibility to the relational databases they were using. And so, we decided to build DSQL kind of to go after both of these problems. As we thought about those, the serverless scale up and scale down, high resiliency problem, and the kind of maximum resilience multi-region problem, it became obvious to us that the ideal architecture we wanted to build for these two use cases was very similar. And so we decided, hey, we're going to go off and we're going to build a new database offering that does both of these things. And that's somewhat challenging, right? It's interesting because at some level, this is a very a set of capabilities aimed at the sort of top end of enterprise capabilities of very high resilience. Relatively few customers have those kinds of requirements, but the ones who do really need it. And then, the serverless capabilities where, we see lots of customers adopting serverless. We see lots of customers adopting containers. It has become, in a way, the way that people build new cloud architectures, especially containers. And then, I don't really want to talk about competitors much. I like to talk about my customers rather than competitors. But what I will say is that, I think it's just super exciting, the amount of innovation that is going into the data space right now. I think obviously relational databases have been around for 40 plus years in one way or another. And it's just so exciting that there is still this big wave of innovation, people really thinking about, how do we make things easier for developers? How do we make things easier for operators? How do we build databases with better properties in various ways? And it's still a really exciting, area of technology to be in.
That makes sense. And so is it safe to say that, like AWS is like, customer centric, and customer is at the center, and everything, like a requirement comes from the customer. So is it safe to say that technologically there was nothing stopping AWS to launch something like this, but probably it was enough requirements coming or enough problems coming from the users? Is it safe to say that?
I think that's mostly right. Yeah, one of the things that technologically we did do that was a big enabler was EC2 time sync service, and so this was a rollout that we've been doing over the last year or so of bringing very, very high quality, 10 to 50 microseconds ability to synchronize time to EC2 instances around the world. And it turns out, for reasons we can get into as we get into the technology, having very tightly synchronized time makes some parts of building a distributed database, and especially getting great performance in a distributed database, significantly easier. And so, we've tightened time sync across EC2, and especially, the latest generations of EC2 instances by several orders of magnitude over the last few years. That's available to all EC2 customers. And that was a very useful building block in us thinking through this architecture. But yeah, I think what you're saying is broadly true. There was no technological reason that we couldn't have started on this journey much or we didn't start on it much earlier. But it was very exciting, right? It's as you say, customer focused, and to hear, hey, AWS has this great database portfolio of lots of different relational and non-relational offerings. But here are these gaps, and our customers really help us understand, where what their needs are and which of their needs we're not meeting. And that's really what drove our development here.
Okay, interesting. I mean, as you said, there are so many things to talk about technically, and I'll get to the time sync feature and why is it critical, how it changes the architecture of the database. Because Google also, or let's say Spanner also uses true time, but there are some other databases, let's say Yugabyte. It doesn't really depend on such a service. So what changes? What complexity is added, stuff like that. We can talk about that. I want to start with another probably interesting question because I've read that this is Postgres compatible, and the SQL engine is used from what is available in Postgres, right? So first of all, why Postgres? I mean, probably I've asked this question like, I don't know, more like 30 or 30 plus times. So probably I know like a broad answer, but what is AWS's answer for why Postgres, and why use the SQL engine that's available? Like, what are the benefits?
Yeah. So I think there are two ways, two reasons for that, or maybe three reasons for that. One of them is when you bring a new database to market, you bring a new database to customers. If you say to them, hey, the only way to adopt this database is to build an entirely new application, it becomes really hard for them to justify doing that work. There are some organizations that are constantly rebuilding their software, constantly building new applications, constantly, replacing things. But the vast majority of software organizations are not working like that, right? They have applications that have built up over many years, sometimes over many decades. In some cases, those applications are the only encoding that exists of their business logic, right? These are the crown jewels of their organization. And going to them and saying, hey, to adopt this new database, you need to replace those and rewrite them, I mean, is unrealistic at best, right? And so, by picking an existing, open source offering like Postgres and offering a level of compatibility with that, you can really accelerate that adoption journey with customers, and you can make the work that they need to do to adopt a new database technology much, much less. So that's one thing. I think the second thing is the parsing of SQL, the planning of execution, the execution of SQL, all of these things that Postgres has spent many years getting great at are both hard to get right, and they take a lot of iteration, and they're pretty great in Postgres. And so what we wanted to do was, leverage those capabilities, limit the amount of stuff that we needed to rebuild and rewrite, and take advantage of that. And the other, and maybe the third one, is, Postgres is for its age and heritage, just a beautifully designed piece of software. It's very extensible. It's a very easy code base to understand. I mean, just given the complexity of what it's solving, it's quite amazing. And so, Postgres was a perfect pick for us because we wanted to deeply replace some pieces of the database, all of the replication, all of the concurrency control, all of the durability, all of the storage, all of the way the transaction sessions are managed, while keeping some pieces. And the modularity and extensibility of Postgres makes that a lot easier than it would be with most of the other, relational open source relational database offerings. And maybe the last one is, we have a great Postgres business with RDS Postgres, with Aurora Postgres, and a lot of operational experience with that. Teams who are deep in that code base, who are actively contributing to the open source code base, are active in the community, and having all of that experience in-house here and that relationship with the community, again, makes it a great pick for something to build on, this component of a much larger system.
Yeah, that's quite powerful. I guessed all the reasons pretty much, like why Postgres, and it's really powerful database. That is also one of my favorite databases. I have most experience with. Sounds good, right? Let's get started. If I have to, let's say, if I look at like very high level, like an architecture diagram of DSQL, what are the core components involved? Because there are so many things happening, like Postgres SQL engine, and then of course there is some time sync service integration. There's of course storage. There's active topology, and maintaining consistency and strong availability. So what are the components at a high level that you would like to draw our attention to?
Yeah. So we can step through that in layers, sort of starting with the client, right? And clients are always important to databases, but probably the least interesting part of the story. Then the client connects to a layer which handles sessions, does authentication, it does authorization, it does session and connection management, it does load balancing and heap management. The next layer down is probably the most critical one, and this is where Postgres comes in, is what we call our query processing layer. And so this is the layer where the SQL is executed, where as we launch support for stored procedures and PLPG SQL and so on, that will be executed. It's the layer where query planning happens. It's the layer where optimization happens. And so the actual mechanics of running a query, running a transaction, running the SQL and its extension languages and so on. The next layer is a layer that handles writes. And that does two important things. One of them is concurrency control, which is this component of the database that does isolation, right? That makes sure that transactions behave like transactions at a particular database isolation level. And then a layer that does replication, which is taking committed writes, making the right number of copies of them, making sure that those copies are distributed to the right places for them to be consumed by the next layer down, and doing all of that atomically. Making sure that when a transaction is committed, it is entirely committed. It doesn't get half committed and so on. And then the final layer is a storage layer, right, where the data resides, and I'll get into into some of the interesting decisions we made there, but also where data access happens. And so when you say I want to get this fact out of the database, it goes down to that storage layer, and that's the bit that's going to say here is the version of the fact that's right for the transaction. And so those are the four sort of broad layers. And TimeSync plugs in at that query layer, and the storage layer is a combination of the database engine itself, the database storage that is doing, responding to queries, looking up facts, scanning over, ordered lists and so on, and something that makes sure that that customer data that's been written to the database remains durable in the long term. It also handles things like backups and so on. And so those are the four kind of broad layers. I think the most interesting ones, I think they're all interesting, but potentially the most interesting ones as we talk through the technology here are the middle two, the query processing layer and the concurrency control and replication layer.
Absolutely. So as I imagine, and I also read in your blog that the query processing layer and the concurrency control and the storage layer, they are pretty much decoupled, and that
Yeah.
allows you to kind of independently scale up and scale down as required, and that's really powerful, right? And then the middle layer, which is the concurrency control, that gives you like the asset guarantees, and and I believe you use the optimistic concurrency control, provides snapshot isolation. And I was reading probably in your blog that like for most applications, the snapshot isolation is pretty good. Like it provides all the necessary aspects. So I want to dive a bit deeper there, and also understand um the like you mentioned like active, and when the data is written, what exactly happens. So I want to start with understanding why snapshot isolation, and then probably go into the right path, like what exactly happens, how
Yeah.
is things are replicated, and making sure they are durable, and how the active topology is maintained.
Yeah. Well, let's talk about isolation. So isolations are really, again, this sort of goes back to the beginning of the concept of what is a transaction in databases, with work that folks like Jim Gray did, decades ago. And the core idea is, if I have concurrent transactions in my database, right, transactions that are running at the same time, what are they allowed to see and do? If they are uh, trying to access the same data in some way.
Yeah.
And traditionally, at the highest end of that is this idea of serializability, right? And serializability is a model, or strict serializability is a model where I can pretend as a developer, as a programmer, that those transactions aren't concurrent. The effects that they have on the database and the effects that they expose to the client appear as though one transaction ran to completion, then the next transaction ran to completion, then the next transaction ran to completion, and so on. Now, that's not what the database is doing, because to get decent performance, the database needs to extract a lot of parallelism from its workload. Unfortunately, that strongest isolation model, as simple a mental model for the programmer as it is from an isolation perspective, forces the database and the programmer or application developer to make a hard performance trade-off. And it becomes quite frequent that one transaction has to wait on other transactions in the system. And so over those decades of thinking about isolation, there's been this development of lots of other isolation levels. There are probably hundreds, maybe thousands of isolation levels implemented or proposed in the literature, all of which make different performance versus isolation trade-offs. And what we've seen is most databases have decided to make their default isolation level something weaker than serializable. Whether that's read committed, repeatable read, snapshot isolation, and so on. And so we picked snapshot isolation because we think that for distributed SQL applications, and in fact for most relational applications, it's something of a sweet spot in that performance and scalability versus isolation spectrum. And allowed us to build our architecture in a way that is really optimized for snapshot isolation, to the point that offering weaker levels doesn't offer much of a performance benefit for us. And so snapshot isolation is weaker than serializability. There's one particular what the database folks call an anomaly or a phenomenon that can happen where you don't get serializable behavior. But it is still a quite simple mental model for the application programmer to think about as they think about transaction isolation. And to get one layer deeper into that, serializability requires the database to make sure that any rows that a transaction has read haven't been changed by another transaction that's running at the same time at the time that first transaction commits. And that's great. Again, serializability is a super powerful idea, but does mean that the chance of that transaction having to block or having to abort on commit increases with the more data it reads, the more it accesses. And so as soon as you do a table scan, as soon as you read a lot of rows from the database, you have this effect where database throughput has to go down significantly. Snapshot isolation, on the other hand, is only concerned with writes, and you create a read snapshot, which means that the transaction sees a consistent copy of the database as a point in time, and in the distributed setting, we can do that with great scalability without very much coordination at all. And then at commit time, or as the transaction runs, you only have to worry about whether your writes, whether the updates you're doing to the database are conflicting with other transactions. And most applications do a lot fewer writes than reads. And so this leads to, for most applications, significantly better throughput and a significantly lower chance of running into contention between transactions, which would limit application performance.
Yeah, I think that's really powerful. And as you rightly said, like most applications are like read heavy. They're not like write heavy, and modifying the same row at the same time, like massively concurrent. So probably snapshot isolation works better. And again, it's a trade-off between performance and the isolation level. And I think that's a fair trade-off in case of DSQL. Sounds good. You mentioned the write path where the SQL query processing is done, and then there is the concurrency control system, and then it is logged, I guess, and then it makes sure that it is replicated, able to replicate it, and then it goes to the storage layer. What exactly is happening within the concurrency control layer? What are the steps involved when I write the data, for example?
Yeah. So there are two things that are happening there, and I think we sort of need to break it down into two parts for the story to make sense. One of them is on reads. So almost all SQL transactions, even if you think they're write only, need to do some level of reads. So obviously anything that's a select has to do a read to the database, but anything that's an update to, updates are read, modify, write. Anything that's an insert where there is a unique index needs to do reads on the database. And so the journey starts with creating a read snapshot. And we do that with a time-honored approach called multi-version concurrency control. And what that simply means is that our storage stores multiple versions of each record. And so as you write a row, instead of overwriting it in place, it says, hey, here's a new version of that row. And so transaction starts, and we get a start time. And this is what we get from our physical clocks. And every read that transaction does to storage throughout its lifetime, it says, give me the state from the database as of my transaction start time, as of this particular timestamp. And what's nice about that is new versions of records can be created by other transactions. They never become visible to this running transaction. This running transaction never has to stop other writers from working, which is great for performance, and still gets a repeatable read, consistent snapshot of the database. Now, I do all my reads and I do my writes. And what we do is that we take those writes and we gather them up. We do this inside the query processor or next to the query processor, and we gather up those writes. And at the time we're doing that, we don't do any kind of coordination, any kind of concurrency control. They're just sort of spooled up locally in the transaction that's running. Then you get to commit time. And this is where we need to resolve the second half of the concurrency control story, which is going to look for what we call write-write conflicts. Like, has another transaction written one of the same rows that we're trying to write since we started? And that is where we have a component of the database called the adjudicator. This is a scale-out, shardable component. And that adjudicator's job is only to answer that question. To say, I'm a transaction. I started at time A. I want to commit at time B. I've written these rows. Has any other transaction written those rows between time A and time B? And so on commit would go to all the adjudicators that are involved in this transaction, all the adjudicators that know about the keys we've written to, and ask them that question. And if all of them say, no, nobody's written conflicting writes, then you can go ahead and commit. And at that point, we can say, at time B, we're committing this transaction. We're going to make it durable in the database. And that's where we write it to a replicated stream, which is based on an internal service that we've been working on at AWS and using in production for more than a decade, called Journal, which will take that write that transaction did, ensure that it is written down atomically, ensure that it is durable across multiple availability zones or multiple regions, depending on the database setup, and then make that available through replication for all of the storage nodes to consume. And so what's interesting about that work or that journey is read-only transactions don't need to do the second half of that at all, right? They just get to commit time. They haven't done any writes, and they can just say, okay, I'm committing, I'm done. And what's cool about that is that there is no coordination required to commit a read-only transaction in DSQL in our architecture, which allows for really great read scaling. It allows us to scale out read replicas of storage essentially without limit. And then the writes only need to coordinate with the parts of the partitions of the adjudicator for the keys they've written. And so if you write only one row or to a few nearby rows, you'll only have to go to one adjudicator. And then there's this next layer that makes sure that once those things are committed, and before we respond to that commit statement, things are written down atomically, durably, and replicated for fault tolerance.
Okay, interesting. I think I understand how this works, and I want to get into the adjudicator component because that's really interesting. So basically, reads are not even having any contention at all. Like they just have, they don't need the second part of it, which is checking with the adjudicator and making sure that there's no concurrent write and a proper lock is taken and whatever. So that is not at all required. And most of the reads, if my application is read heavy, no contention at all, and you can just scale, because it's separate component altogether. You can just keep scaling the processing engines, the query processors, and that's it. You are done, right?
Yep.
For writes, you mentioned that everything is done atomically, and what we mean by that is you write to a journal, which is like a replicated stream, to make it available to other replicas for durability and high availability. Um, how is that atomic right maintained? Like, how is that atomicity maintained? What exactly do you have to make sure to that it's correct, in the sense that if you write to that journal but there's no acknowledgement, for example, what happens, because that data would be replicated? Is it just some you using some flags to denote that this is still not committed, or what exactly happens there?
Yeah, that's a great question. I mean, the hard part of any kind of distributed replication is dealing with those failure cases,
Yeah,
and especially dealing with un um, the implicit failure cases. Like, hey, I tried to do this and I just got a
yeah,
timeout. Like, did
yeah.
it happen or not? Well, I don't know. Um, and so from the replication perspective, there are a few things that can happen. The first one is you call journal and you say, write this blob of data for me. And it says, yes, done. Easy, done. Okay. It can say, no, I can't do that for whatever reason. Again, easy, done. You don't like that because it's a reduction in availability of the system, but it doesn't have any safety properties. Then, there's a case where you start, sending that data to journal, and on the client side, on the producer side, you crash or timeout or something. And then finally, there's the case where something happens on the network between them, and so you send that final byte. You say commit to the journal, and that you don't get a response. And this is something that we've spent a lot of time on, and was one of the huge benefits in for us for building on this journal that we've used in S3. We use it in DynamoDB. We use it in Kinesis, kind of across AWS's data portfolio, um, because we've had time to really work through those edge cases, really design those protocols. And so I can't really go into the detail of exactly how that protocol works. But there are two things there that are important. One of them is, yes, it's broken up into pieces, and you have to have this kind of final trailer saying, okay, we've all agreed that this is now durable and atomic in the journal. Um, and to make sure that protocol is right in all of these strange failure cases, we've spent a lot of time on formal modeling. We built models in languages like TLA Plus, in P. We've used formal tools on the Rust code that the stuff is implemented in, to make sure that those protocols are safe, have this effect, this atomic effect, have this durable effect that we depend on, no matter what those failure cases are. And then finally, sort of looping back to that failure case, there is always in any kind of system, mostly in distributed systems, but this happens in single systems too, there is a case where clients call commit and don't get a positive acknowledgement back and don't know whether that is committed. And so, as system builders, we try and make sure that happens as little as possible. But that is a case that the clients have to be able to deal with. There is always this case that you pointed out of commit. Yeah, I don't know if it happened. And that's where, designing schemas for idempotency and so on becomes, this really great kind of additional fault tolerance tool to use, even on top of a database that is designed for maximum fault tolerance.
Okay, interesting. The next part that you mentioned was about, during the commit time for writes, you asked the adjudicator that, hey, is there a new write after this timestamp or something? First of all, how does the adjudicator know? And second, how is that lookup, performance, so that it doesn't become a bottleneck for write path?
Yeah, and the answers to those are actually closely related. What our adjudicators do is store, mostly in memory, but also on some fast storage, um, essentially just a version map of, you know, during a time window from a beginning time to an end time, which versions of this data have I seen exist? And so, for example, if a transaction comes along and says, well, I started all my reads at time 1 and I want to commit at time 5, the adjudicator then looks at that in-memory map and says, okay, for those rows, I have a row for time 4, I have a row for time 3, those are okay, right? No, actually, no, they're not okay. They were after your start time, and so I have to reject you. And so by keeping that in-memory map, it's just a map of essentially keys to versions in an optimized data structure and for a time window. And one of the trade-offs that we make in distributed SQL, in Aurora DSQL, is that transactions have a limited runtime. We don't allow transactions to run more than 5 minutes. And so the adjudicators only need to store about a 5-minute window of version data. Anything older than that, they'll say, no, you've exceeded the transaction time, and so I'm going to reject you out of hand. And anything newer than that, it has that data. And then as it makes that decision to say, should this commit, it can update its data to say, well, I've seen a newer version. I've said yes to it. And so that version exists now. And so I'm going to remember that fact. To make that fault tolerant, we also replicate that data. That is soft state. It's not data that actually needs to be durable in the database. But it's state that we send, across multiple hosts to make sure when, one adjudicator fails, we can immediately replace it with a hot standby that can answer those same questions in a consistent way. But from a safety perspective, the adjudicator always has the option to say, I don't know, reject that transaction. You don't want to do that because it's bad for availability, it's bad for liveness. But always from a safety perspective, it can have this option of saying, well, I'm actually missing some facts about the world. I don't know what the latest version of that key is. You haven't given me no option but to say no to that transaction.
Yeah, very, very interesting. So by this 5 minutes upper bound for any transaction, you kind of limit the size of the data that has to be stored in memory for the adjudicator, right? So that's very interesting, and that makes it efficient as well, because first it's in the fast memory, and second it's not a ton of data. You also mentioned there are multiple of these components, adjudicators, right? Um, how is it distributed in terms of the concurrency control component? Is it closer to that? Is it a separate component altogether? Or let's say, how do you know which adjudicator to talk to? Is there a leader? Is there, like, I don't know, like a load balancer? What exactly is happening there?
Yeah, so you can think about having a key space, right? Like here are all of the possible keys in my database. And at the adjudicator level, we carve that key space out into slices. And at any given moment, there is a single adjudicator that is the leader for that slice.
Mm.
Now, there can be as many slices as you want, right? That key space is potentially very big. If it's a UUID, it's 128 bits. And so, you can slice that into lots and lots of slices. But for a given slice, at any given moment, any given timestamp, there is a single adjudicator that is the leader for that that moment. It can hand over that leadership either because that slice has become too hot and it wants to split it, or that slice has become cold and it wants to merge it with some of the ones next to it and hand over ownership, or it's failed and it wants to hand over that work to another adjudicator, or another adjudicator wants to take over. But at any given commit time, there is a single adjudicator for any given row that is the leader. So lots and lots of leaders in the system at any given moment. There isn't one global leader, but there's one leader per row. And so you need to make sure that you hit that one. And that becomes a metadata distribution challenge, one of the cool things in relational database design, and one of the cool things that things like Postgres do, is there's a catalog table. It's right. It's the system table. It's kind of hidden, not entirely hidden, but kind of hidden from the user. But for all other perspectives, it is a normal table in the system. And so we can use that catalog table to write down at every moment who is the adjudicator. And so taking over, splitting a slice becomes a normal transaction that goes through the normal transaction path of the system. It updates that catalog table. It's this great simplifier, right? Because we're using the database itself to store that data about how things are split. There is a slight sort of immediate discovery problem, a sort of initial kind of bootstrapping discovery problem, but you can do that on the read-only side. And then the final part of that protocol is if you come to an adjudicator with stale information saying, I thought you were the leader, that adjudicator is required to say, no, I'm no longer the leader. You have stale information. Go back and try this transaction again with an updated map of adjudicators. And so that's where there's the strong leadership election protocol that makes sure that at any moment, if an adjudicator is going to respond at a timestamp, at a commit time, there is exactly one adjudicator that can make that adjudication. Or actually, to be more specific, at most one adjudicator. You can't have exactly one in systems like this. It's just not a possible thing.
Yeah. Yeah, I think it's interesting. Anything more you wanted to add there?
Yeah, and just sort of looping back to the 5-minute thing. I think what's really interesting there is, databases are this extremely trade-off rich space, right? And so we get huge performance and scalability and system simplicity benefits out of 5 minutes, out of having that 5-minute limit. We may have time to get into detail on this, but we avoid one of the big pain points that folks have with Postgres, which is vacuum, again, just by taking advantage of that 5-minute limit. But in exchange for that, it means that you can't have these very long-running transactions, which are useful for some kinds of applications. And I think it's a great example of how the database space is this very trade-off rich space. And there are, trade-offs that are great for some applications. And we've made ours carefully that aren't universally good for all applications.
That makes sense. And I love that phrase, trade-off rich space. I'm going to use that somewhere. Cool. That makes sense. And I now understand the adjudicator part of things. We talked a bit about replication, but at a very high level, right? And we commit a transaction, let's say, in a journal, and then replicate it streams. Are these two different components, by the way, or is the same? Like journal contains the replicated streams as well.
Yeah, it's both the replicator and the atomic committer.
Okay.
And those two problems are deeply tied together and are hard to separate. So everywhere else in this architecture, we've really tried to disaggregate individual concerns into separate components for a whole bunch of good reasons. But those two are deeply tied together because of the kind of physics of the problem. The ideas of atomicity and durability are hard to separate in a database architecture.
Yeah, I think it makes sense. Talking about imagine a multi-region deployment where I want to have an active deployment. Once data is written into the replicated stream, how is this replication exactly happening? And when do we say that the replication is let's say both the regions have equal amount of data and there's no lag, so to say? And if there is at all a lag, how is it handled?
Mm-hmm. Yeah, so the setups that we support today, and I think over time you can expect more flexibility in these setups, but the setups we support today with D-SQL have two primary regions and a witness region. And we consider a transaction durable when it is in storage across multiple AZs in at least two of those three. 2 of 3 is really nice because it's in the happy case is a really nice latency optimization property, and in the failure case allows you to have exactly the same durability properties even when one of those 3 regions is disconnected or failed or unavailable or whatever. And so the commit before we say a transaction is committed, we will make sure that it has been written in the region it's committed in, and at least one other, and that will happen synchronously before we say yes, your commit has succeeded. Now, if one of those 3 regions starts falling behind, right, like let's say there's a lot of packet loss, or somebody's driven a backhoe through the network or whatever, right? A lot of backhoes. These networks are highly resilient. What's going to happen is that the other 2 regions will be able to continue to offer high availability, high performance, strong consistency, all of this good stuff to clients that can talk to them. And the region that's falling behind and isolated is going to initially start to offer worse read performance because it has to wait longer to make sure it's seen all the writes in the system. And then once it passes some threshold of being behind, will start to be unavailable from the perspective of clients in that region. And so this is the hard law of physics. I think this is the one that folks are mostly referring to when they talk about the CAP theorem, is that once that region is in effect disconnected, it's far enough behind, the packet loss is too high or 100%, that region becomes unavailable for further transactions. But that doesn't mean the other 2 need to be unavailable. They can continue to be available, consistent, fault tolerant, durable, all of that good stuff. Then, let's say the network heals, which they do eventually. The replicated data will again start flowing into that region. It will take some time for that region to catch up, to make sure that it has seen all of the written data. And as soon as it's caught up, which happens entirely automatically and internally in the system, it will become available for writers and readers in that region again. Now, what's different about our system, because it's a 2 of 3 synchronous system, there isn't a case where there are writes that exist only in that one isolated region, because they never would have been written there because they couldn't get out to the other 2. And so any write, when a region gets isolated, there are 2 cases. Either it contains no changes, or if it does contain changes, those changes also exist in one of the 2 other regions and can, flow to the right place. And that's required for strong consistency in this form of system. And what I will say, I think, is, one of the reasons that we really like active-active as an architecture, and that I really like strong consistency in combination with active-active, is that it makes the semantics of that recovery much simpler, right? In asynchronously replicated systems, there is some time during recovery when the regions that have come back up need to reconcile their writes with the writes that are in the other region. In a strongly consistent system like DSQL, that doesn't happen because there are no writes in that minority region. None of them have been accepted on that small side of that single region partition. And it makes the semantics of that recovery really simple to understand from the client's perspective, and easy to get right from the database builder's perspective. But again, trade-offs, right? And the cost of that is the latency of synchronous replication.
Yeah. I think that makes sense, and it's a good trade-off. Like for most applications, that would just work. In your blog, I guess you mentioned that when there is a partition like this, like one region is not at all available, since the data is all replicated, you don't have to do anything. It's ready to serve. And that's what active probably means. Uh, Except the part of adjudicator, which you have to, move to the other region. Is that correct, or my understanding is different?
Yeah, so the adjudicators, and that's where that's where a switchover has to happen,
Hmm.
and that's why it's so important that that adjudicator state is soft state. It's
Hmm.
not the durable state of the database, uh, and so the way that that happens is that adjudicator that is in an adjudicator that's whose leader is in the region that just went down. That leadership will go away because that region can't talk to the other two and run the leader election protocol. Another adjudicator will come up in one of the healthy regions because it can run the leader election protocol, and it can look at the state in the database, look at the committed transaction log, and exactly reconstruct the correct state just from that committed transaction log. And so while the adjudicator only works on in-memory state, only works on transient state and isn't durable, the state that it does have can be exactly recreated from the log of committed transactions as that takes over. Uh, so that state is transient and it's very small, which makes that sort of failover and recovery portion very, very fast, right? You don't have to copy the bulk data of the database. You only have to learn about a small window of very recent transactions.
Interesting. And that's when again the 5 minutes thing is beneficial, because that has an upper bound to keep that state really less in terms of data. That makes sense.
Yeah, that's exactly right. And the other, the other cool thing there is that you can take advantage of temporal locality.
Mm.
So it turns out that when folks access database rows, they tend to access those rows. Um, a row that's being updated is quite likely to have been updated recently, whereas a row that was updated a year ago is quite unlikely to be accessed, updated now. And because of that temporal locality, as that new adjudicator rebuilds its view of the world, it can start filling in those I don't knows with here I know about this latest version in kind of backwards time order, starting at the current time and going backwards towards that 5 minute window. But very quickly, it will fill in the most relevant ones because the most relevant ones are likely the ones that have been accessed most recently.
Yeah.
And so that's a cool kind of application of this, the sort of core computer science idea of temporal locality.
Yeah. That's very interesting. I have one more question on the fault tolerance part, and then I want to move to the upper layer, which is the SQL or the processing layer. So you mentioned there are, like, typically there are two regions, and one is the witness region. But
Mm-hmm.
when one of them is gone, there are only two regions now, right? Is there like a what happens to the witness region then? Like, is something changing? Is there like a new, or is just waiting on the unavailable region to come back?
Yeah, it's just waiting on the unavailable region to come back. And so right now, we don't support promoting a witness region to a readable primary region.
Mhm.
Um, I don't want to talk about the roadmap too much, but I think that's something that folks might be able to look forward to.
Yeah.
But essentially, what happens is that if one of the primary regions is the failed one, the primary region, the healthy primary will continue working. The witness region will continue being its witness region, and that 2 of 3 commit will essentially become a 2 of 2 commit, right? Because you have to, the third one will never work.
Mhm.
Uh, and similarly, if it's the witness region that becomes unavailable, well, that will be completely invisible to clients on both sides. We will sort of go to a 2 of 2 commit. Maybe there'll be a slight latency increase because that witness could be closer to one of the two regions. Um, and it's just a matter of waiting for that to recover, and then it'll get caught up by the journal replication and become a full a full sort of participant again once it catches up.
Yeah, that makes sense. Um, we talked about reusing the SQL engine of Postgres and then separating it out from the actual concurrency control and storage mechanism. Gives you the ability to scale out reads and scale out the SQL processing independently. So I want to ask you, like, what is the role of Firecracker VM in there? How significant it was?
Yeah, that role is super important. And so Postgres is, as I said, a great piece of technology. I've got a huge amount of respect for, um, but it is also a vast C code base, and just from a security perspective, uh, in a multi-tenant system, you need to make sure that there's a layer of isolation around it. In RDS and in Aurora, that layer of isolation is an EC2 instance. And so every database runs on its own EC2 instance, and we get strong isolation that way. But in DSQL, we needed something that was more dynamic because we needed to be able to scale up in milliseconds. And we wanted to build something that was finer grained, that would allow us to um, because we're going to scale up over multiple hosts, we can have those query processes running on lots of hosts in the fleet. And so we want to run a lot of different workloads. And that's where, Firecracker was a perfect fit. Firecracker is this micro VM hypervisor that we built for Lambda, for containers. We've used all over the place in AWS over the years. But it allows us to run a very large number, hundreds to thousands of strongly hardware virtualization isolated guests on a single machine. And so every session in DSQL is assigned to a Firecracker running the Postgres engine inside that Firecracker. So that provides strong isolation around the Postgres engine because it's hardware virtualization, and the ability to create new ones very, very quickly. And we create new ones very quickly by, we don't want to start up and boot up a micro VM and then start up Postgres. And so instead, what we do is we start up boot up Linux, we start up Postgres, we start up all of the user space stuff around that, and then we take a snapshot, a copy of the memory and register state of that VM. And then when a connection request comes in, says, hey, I want to connect to the database, create me a new session, we can restore a Firecracker from that snapshot really, really quickly. In some cases in single-digit milliseconds, and save a huge amount, even over the relatively fast boot time of Firecracker. That helps with density too in a bunch of interesting ways. And so Firecracker, I think, is this really cool piece of technology and really enabling for these kinds of architectures, makes scale out a lot easier without having to make any compromises on the security and isolation properties of the system, which are, always goal number one for us at AWS.
Yeah, that's very interesting. So just to understand a bit more, so just to avoid that, let's say someone is trying to create a new session and you don't have to boot up a VM and bring up Postgres and all, you maintain a pool of, let's say, VMs, and then as soon as a new connection or let's say session is to be created, just pull up that or kind of reuse something from the pool, right? And so it avoids, let's say, a cold start problem.
That's right.
Okay, interesting.
And then, once that session is complete or that transaction is complete, that Firecracker will go back into the pool, but it will go back into the pool that will only be reused for that same DSQL cluster. And so once it's been, touched by one cluster, by one customer, it won't be used again.
Mm-hmm.
But, we can do that because creating new micro VMs in that pool is very fast and very cheap. And so, we'll keep that around for a while. Another session might come in for that database. But if it doesn't, it's not a hard decision to say, well, we're going to tear it down. It's a few milliseconds of compute, and then we can replace it with a new one, a fresh one, if if a new connection request does come in.
Okay. And is there any movement while the session is active, just to scale up? For example, let's say if I have a session and um, my current workload needs to be scaled up. So is it just that new sessions will be created and more micro VMs will be allotted, or it's just like more micro VMs, right? That's the
Yeah, you'll get more
scalability
micro
bottleneck.
VMs.
Okay.
But obviously, if the SQL inside your session requires more memory to execute, right? It's got a bunch of transient state, it's doing a big join or whatever. We can also vertically scale that
Mm,
particular micro VM to, as the needs of that workload increase, as the needs of that session increase,
mm.
and then scale it down, reclaim the memory, reclaim the CPU. As the workload completes, or you've done with that big join, you're done with that big temporary response data set or whatever.
Okay. Pretty interesting. Um, since you have this, decoupling between the query processing and the other layers, uh, does this also enable you? So one advantage is definitely that you can independently scale up and scale down, and let's say for reads, you don't have to, the performance can be really high because you don't have any contention. It's all um, uh, disaggregated. um, does this decoupling also provide you the benefit in future if you want to support, let's say, another SQL engines, I don't know, like MySQL or something like that? Or there is still some coupling between how the query processing works and how the storage is laid out, and probably with MVCC or the isolation, is there something like that?
Yeah, that's really interesting. I can't really talk about the roadmap, but certainly we were very thoughtful when we designed the storage APIs to make sure that the things we were doing weren't Postgres specific. Um, there are a few reasons that was easier to do with Postgres than maybe some of the other engines that are available. A lot to do with Postgres's extensibility and the kind of modularity of that code base. Um, but we were careful, and this is this kind of Amazon idea of not going through one-way doors. We were careful as we designed those APIs and designed the core architecture to make it possible to support other engines in future, as we hear from customers about what they need. Postgres is rightfully, very popular at the moment. It's getting it's really having a moment as a database, and it's great to see because it's a technology I love. Um, but there are also folks who've made other choices over time, and would appreciate the feature set, and so we're always interested in hearing from them. And I have no doubt that the next hot thing is going to be something else. That's the nature of the industry we're in, and so we really tried to optimize for being able to adapt over time as our customers' needs change. And if customers come and say, "Hey, there's this other SQL engine that we really want support for," then that's something that we can add.
Interesting. Yeah, that sounds really powerful. But again, depends on what is the ask from the customers, how popular is the other technology, and but technologically there is no coupling or no limitations. That's what I get.
Yeah,
Awesome. For So talking about the use cases, like probably anyone who needs, let's say, a global availability and really super high availability, multi-region active deployments, probably this, and of course the asset transactions and strong consistency guarantees, probably Aurora DSQL is the right choice.
yeah.
What are other use cases? Like, how should I go about thinking that, oh, is Aurora DSQL the right choice for me? What are the current problems that probably can be solved by Aurora DSQL? Or and I also want to ask you the inverse of it. When is Aurora DSQL not a great choice?
Yeah. Yeah, but both great questions. So as you say, those active multi-region things are one core workload. I think the other one that's a great fit is, just microservices and services written using serverless, using containers. You know, the ability to scale up comes with the ability to scale down in our architecture, the ability to handle, highly spiky and seasonal workloads. And so we think it's a great choice for services in SOA type architectures, microservices in microservice architectures. Hey, that little toy app that you're putting together with Lambda and API Gateway, and it's just because it's a there's a hands-off operational model. Because it's scaled down, because it's very easy to think about the operations and the scaling properties. And I think it's going to be a great fit for those kinds of workloads. I think it's going to be a great fit for a lot of kind of line of business service workloads that need a transactional database, where the teams that operate them don't have a lot of database operations experience, right? They aren't DBEs, they aren't DBAs, right? They don't have this background in running a database. And so we'll really appreciate the hands-off operations and kind of built-in scalability, built-in fault tolerance, built-in patching and versioning and other things we've done with DSQL. So it's not only about those large scale and multi-region workloads. I think it's a great fit for a lot of smaller workloads too, and growing workloads, right? We want to minimize regret, right? We wanted to say, here's a database you can pick when your application is tiny. You're doing a transaction a day, and as your business grows, it's going to grow with you, and you aren't going to have to worry about doing a migration. Because there's nothing more painful for a business owner to hear from their engineering team than, well, we've got all these customers lined up, but we've got to turn them away because we can't scale our database. That's a terrible place for everybody to be in, and I've been there in my career, and I hope to never be there again. And that's one of the things we were trying to bring to folks. The other part of your question, like why not, right? Like obviously exact compatibility is one, right? Like sometimes you need compatibility with Postgres, you need compatibility with MySQL, and there Aurora is a great bet. Or maybe you've built on Oracle or Microsoft SQL Server, and their RDS can be a great choice. There's some workloads for which a NoSQL model like DynamoDBs is a better choice. There are workloads that are a great fit for vel keys, in memory, rich data structures, and memory, the durability and multi-region capabilities that MemoryDB brings to that. And so, so it's mostly about what do your application developers need, right? Like, what does your application need? What is the right data model for that? Is it NoSQL? Is it document? If it's SQL, then we would love DSQL to be the default there, but maybe it's an exact flavor of Postgres. Maybe you need that one particular point release of MySQL for this application to work, and that's where Aurora or MySQL can be. Or Aurora Postgres, Aurora MySQL, or RDS Postgres, or RDS MySQL can be great choices. And then there are other great choices in the market. And so, again, I think this is a sort of trade-off rich space. But what we've tried to do here is build a database that is a low regret, easy decision to make default choice for applications of all sizes that need a relational feature set.
Awesome. That sounds really good, and that was also my understanding after learning more about the database. In the interest of time, we have to stop here. Otherwise, I have like tons of many questions I can ask you. But thanks a lot for joining me today and sharing all the amazing insights about the database, about general database trade-offs and concepts. It was a really good learning experience for me, just talking to you, and I'm really excited to publish this episode pretty soon. So for
Yeah.
our viewers, please do follow Mark. His blog is amazing. I'm going to attach a link in the description so you can all learn. But yeah, thanks a lot for joining me.
And thank you so much for the opportunity. I mean, it's always just super exciting to talk about this whole space. There's so much fun stuff going on here.
Absolutely.